today. We're going to talk a little bit first about uniqueness and shore up some more ideas about combining asymptotic expansions, how to create asymptotic expansions of different functions and asymptotic series. And I think we should get most of the way today to sort of finishing up just our general mathematical framework for asymptotic series and sort of set the stage for asymptotic approximation of integrals next week. And then that module will kind of last for a few weeks, and then we'll get on to differential equations, and that'll kind of be the remainder of the course. Okay, so last time, just a quick recap, we talked about properties of order relations, right? And in general, an order relation is something like f is big O of some function g, okay? There's several ways of combining these. Summation, you can apply power series, integration, and so there'll be some practice problems on homework 2, just sort of identifying order of asymptotic expansions of particular functions of epsilon as epsilon goes to 0. I want to say a word about uniqueness. So asymptotic expansions, asymptotic approximations are unique for a particular sequence, okay? And this is an important point, okay? So for instance, d n of epsilon, right, may be something like 1 epsilon, epsilon squared, epsilon cubed, so on and so on. It may be something like log of epsilon to the minus 1, log of epsilon to the minus 1, as we've seen before with transcendental equations, okay? So that's the point, is that for a particular sequence, right, the coefficients of this sequence should be the same. You can't create a different asymptotic approximation using the same sequence, but sort of changing the coefficients, okay? But you may have, two different or more asymptotic approximations that involve different sequences, right? So you could expand asymptotically in a power series of epsilon. You could expand asymptotically in some transcendental function, okay? So, but in general, for f asymptotically approximated by some an dn epsilon, okay, we can obtain this coefficient ak if we take the limit as epsilon goes to 0 of f of epsilon a minus the sum from n equals 0 up to k minus 1 a and delta n of epsilon divided by delta k of epsilon. Okay, so that should extract for you the particular coefficient that you need to use for this term in your asymptotic series. Okay, so functions, okay, as we were saying, can have different sequences. And just to make this concrete, let's consider the following example, right? Tangent of epsilon, we could, of course, use the Taylor series, okay, which would be epsilon plus epsilon cubed plus 2 epsilon to the 5th over 15, so on and so on. Let me write this as this is our asymptotic approximation or expansion. We could also expand in sine of epsilon plus 1/2 sine of epsilon cubed plus 3/8 sine of epsilon to the 5th, right? You can imagine you could do this with, for instance, a change of variables, right, where you made y equal sine of epsilon, and you rewrote this as a function of y, and then did that Taylor series. You can also expand in hyperbolic cosines, square root of 2/3 epsilon plus 31/70 epsilon hyperbolic cosine of square root of 2/3 epsilon squared plus so on and so on. Okay. Not showing you how to get those. You could get them using this sequence and then performing an expansion. You could obtain some of these through iteration. Okay. But the point is, notice that tan of epsilon does not have a unique asymptotic expansion in the sense of, there's only one particular sequence you can use, right? There are typically myriad sequences that you could use, but when you pick a particular sequence, right, epsilon 1, epsilon, epsilon squared, epsilon cubed, the coefficients will be the same. Okay, that it's unique up to its sequence. Okay, so the other thing is that two functions can have the same asymptotic approximation. Okay. Why is that? Well, one way that it could happen is that if you just add on something that's not even of the order of any terms in your sequence. So let's consider e to the epsilon, right? That's just got a power series that we can get through Taylor series expansion, okay? For one particular asymptotic approximation. But if we add on e to the -1 over epsilon, that's going to be smaller than any of the terms in this series, okay? So that means it's going to have the same asymptotic approximation in this particular power series, okay? There are other ways to get, same asymptotic approximation for two different functions, okay? But this is just one because this essentially has order, okay, that is smaller than all of the terms in this sum, okay?
Would the second one break down quicker, like as epsilon's getting larger? I should say the first one works well for epsilon up to this threshold, but would the second one work worse at that threshold?
Well, in the limit, right, they're going to have the same order of accuracy, right?
Right.
But for sure, yeah, you can't really say much of anything once epsilon starts to get big. Like, yeah, if epsilon goes up to 1, right, this is going to be more accurate than this. Yeah, okay. You could say that. Asymptotic approximations, okay, they can be added, right? So if you have two asymptotic approximations that involve the same sequence, right, you can just add the coefficients of the sequence. You can subtract, right, by the same principle. You can also multiply, and you can also divide them, okay? But care must be taken when substituting in, okay? So for instance, if I have one asymptotic approximation and I write down some recursive function, you know, f of g of x, for instance, okay, I can I can try making a substitution in, right, but then I may need to expand, right, or I may need to respect the order of the particular arguments, right, that I'm taking the limit. If I made an asymptotic expansion assuming something about the size of the argument, I have to worry about that when I'm substituting an expansion in as that argument. Okay. They can also be integrated term by term. Okay. But problems arise, okay, if you try differentiation. Okay, so let's let me see what I want to do here. Okay, let me back up. Let's keep that for now. Okay. So for instance, right, we can look at a few examples, okay? And if so, for instance, if we recall our order relations, okay, we'll look at a few situations where we have to take a little bit extra care when considering substitution, okay? So let's say that we have some function f of z just equals 1, and then g of z equals e to the iz, okay? Then it turns out f of z is equal to big O of g of z, right? As z goes to infinity, and for z positive in this case. Okay? But the integral from 0 to z of f of x dx is not equal to big O of the integral from 0 to z of g of x dx as z goes to infinity. Okay, so because the problem is, right, this integral is going to blow up, right, and then this integral is going to stay finite in this case. So the way to fix this is just to take magnitudes, right? So if you remember, when we sort of integrate these order relations, we have to take magnitudes of our functions. So f of x dx, that's already just a real number, okay? But our exponential involving the imaginary coefficient, we have to take the magnitude of it, okay? And then we're just going to have 1, and it's going to have the same scaling now as the integral of 1 as z goes to infinity. Okay, that's integration. Okay, now let me point out why differentiation can be a problem. Okay, so for each, let's say, mu in the reals, okay, I can write down the sine function with mu as a coefficient, And this will for sure be big O of 1. Why will this be big O of 1? Well, because the amplitude of this, right, never gets bigger than 1. Okay, as z goes to infinity, okay, and z is greater than 0. Okay, but what happens if I try and differentiate? So if I take d mu of sine of mu z, then what comes out is z cosine of mu z. Now I have z as my coefficient here, and that's going to blow up as z goes to infinity. But if I differentiate 1, then I get big O of 0, okay, which is not true. As z goes to infinity, z greater than 0, okay. So this demonstrates a counterexample to, trying to use differentiation on these order relations, okay? So it's sort of easy to see now, but in the heat of battle with a problem, sometimes it can be easy to forget, right? And sometimes it'll work, okay? But there's plenty of cases where it will not. So it's not really a feasible argument in general, okay? So differentiation with respect to parameters does not preserve these order relations, okay? So, but it will work if your function is analytic in the limit variable, okay? But that's a problem with the above examples that you don't have that. Okay. All right. So another example.
Are you saying sine of mu z is not analytic with z?
The z cosine of mu z.
That's not analytic?
Maybe I have something wrong here. So I'm going to correct my notes here. So yeah, I mean the problem is if you go, you can't formulate an expansion right around infinity.
Ah, okay. Yep.
Yeah. So it's fine with respect to z, but the question is it analytic with respect to the limit? Yeah, that's what I mean. All right. Okay. Another example. Okay. Let's take z sine of 1 over z. Okay. This is going to be order z as z goes to 0 from above, let's say. Okay. Even though this is wildly oscillating, the coefficient is vanishing. Okay. Or z lives in R. Okay. Now, if we differentiate with respect to z itself, what do we get? We get sine of 1 over z, right? That's going to wildly oscillate. And now we have cosine of 1 over z divided by z, okay? And this is unbounded as z goes to 0 from above, okay? Or from either side, I guess, okay? So again, this does not preserve our order relations, okay? And so you cannot necessarily differentiate with respect to your function variable, right, in addition to the parameters, okay? So again, let's ask, when can we differentiate, okay, order relations, okay? And so as we were saying, we can do it with respect to the parameter if our function is analytic, okay, and our limit, okay? And we can also do it with respect to the limit variable if the function is differentiable and it has an analytic power series, okay? So and the issue with the last example, one of them is that that function is not going to be differentiable at 0, right? The derivative is going to blow up, okay? So that's a word of warning about differentiability, okay? You can sort of stay away from it entirely, or you can ensure that your function is sort of nicely behaved when you differentiate it and in the limit, okay? So that's a bit about order relations, okay? A word of caution about them, okay? In the time that remains, I mostly want to go through kind of a curious example of an asymptotic expansion credited to Euler, as a great many things are, okay? To give some intuition for what's actually happening with asymptotic sequences in terms of what they mean and how they sort of can decry intuition at times, okay? So I want to consider the following asymptotic expansion, okay? So I'm going to call it S of X, okay? And it's going to look like this: 1 minus 1 factorial x plus 2 factorial x squared minus 3 factorial x cubed, so on and so on, is equal to the sum from n equals 0 up to infinity of, it's an alternating series, right? But the coefficients are getting larger, okay? And x to the n. And notice that this diverges for x not equal to 0, right? Does this series even have any meaning? Okay, let's dig a little bit more into it, okay? So Euler considered this series scaled by x, okay? And then wrote down the following differential equation. So if I take the derivative, right, of phi now, I'm going to get 1 factorial, okay? Is that right?
I think you get
Yeah, 1 factorial, yeah. Right, yeah, because I differentiate that, minus 2 factorial x, right, because now I'm bringing this power down, plus 3 factorial x squared minus so on and so on, okay? This is also equal to x minus phi of x divided by x squared, okay? So fine, okay? So now I have a relationship between phi prime and its derivative, okay? Now I can solve this differential equation. It's just a linear differential equation, single variable. We can use integrating factor, okay? And right, if we scale by our integrating factor here, e to the integral of 1 over x squared, then we get phi e to the minus 1 over x prime is equal to 1 over x, e to the minus 1 over x, okay? Write the solution now as phi of x equals e to the 1 over x integral from 0 up to x e to the minus 1 over t divided by t dt. Okay. So phi, okay, seemingly can be written as this function here, right? Even though it's comprised of x times some divergent series, okay? Let's take it a bit further. If I perform a change of variables, okay, what Euler found was that s of x is equal to phi of x over x. Okay, if we perform that change of variables now, I get e to the minus w divided by 1 plus xw dw, okay? And this, in fact, is an analytic function of x as long as we're not living on the negative real line, okay? And excluding 0 as well, okay? So I have an analytic function here, okay? But I represented it with this thing that looks like an asymptotic series that essentially diverges, okay? And the gist here, right, is that you know, whether or not a series diverges or not is not necessarily a good guide to if it's informative, okay? So moreover, right, if I assume that I can compute this divergent series, the value of it, by just evaluating this integral, okay, then I get some interesting relations, okay? So s of 1 equals 1 minus 1 factorial plus 2 factorial minus 3 factorial plus 4 factorial, okay? If I evaluate that integral, I get the relationship that this is 0.596347. It's some irrational number, okay? Curious, okay? So we'll get to what's under the hood here. I also want to point out another derivation that's more descriptive for us. And so those of you that have seen the gamma function before, I mean, I think in PDEs we talked about this, okay? The gamma function is gamma of n plus 1, right? You can use it to represent factorials. It's written as the integral of e to the minus t t to the n dt. It's sort of like, extending the factorial to just the reals, okay? Well, we can also represent s of x in terms of the gamma function, and you'll see the gamma function come up a lot in these methods for integrals that we'll talk about next week, okay? But if I write out, okay, that sum that represents this sort of Euler series again, I can write it equivalently as -1 up to the nth power. Now the integral from 0 to infinity of e to the minus t, and now I'm going to group together the x and the t there, dt. Okay. If I swap the integral and sum, okay, of course, we may worry about whether convergence is satisfied. Remember, we said that it's not, but let's just swap nonetheless. We get that same integral that we wrote down before by applying geometric series, okay? Because 1 over 1 plus xt is equal to the sum from n equals 0 up to infinity minus 1 up to n xt and to the n if xt has magnitude less than 1. Okay, but remember this integral, right? I've sort of done something slightly abusive because this integral, right, takes t all the way up to infinity, right? So technically, this should only be valid for as x goes to 0, right? Because because I'm taking the product of x and t. Okay. So is this just total garbage, right? I mean, I've derived something, but clearly I've made a couple leaps which I shouldn't necessarily be able to make, right? So the question is, how does s of x, okay, which is divergent for x not equal to 0, represent this function f of x, which is equal to the integral from 0 up to infinity, e to the minus xt over 1 plus xt dt. Okay, question mark. Okay, and in fact, if we note that 1 plus xt is equal to n equals 0 sum all the way up to, not up to infinity, but just up to m of minus xt to the nth power. The remainder of this you can show is minus xt to the m plus 1 power divided by 1 plus xt. So m equals 0, 1, 2. This is true for all those. And this is exact. And you can check this yourself. Okay. So I can write f of x as the sum of something I'll call Sm of x and Rm of x, okay? Sm of x is going to be a partial sum, n equals 0 up to m, minus 1 to the n factorial x to the n. And our remainder is going to be minus x m plus 1 integral from 0 up to infinity, e to the minus t, t to the m plus 1 divided by 1 plus xt dt, okay? So again, even though I have a series that's divergent, it turns out I can sort of truncate this into a partial sum, and the divergence in the limits, okay, is apparently not so much of a problem. Okay, this still provides an accurate representation of this integral that I have here. Okay, this common integral that actually comes up a lot, right? So this should tell you that often there can be, non-intuitive things going on with asymptotic series, okay? Because convergence in the limit of many, many terms is not necessarily the premium, right? Because you're typically only going to use part of a sum, okay? And if that partial sum works relatively well, okay, you shouldn't be so worried in terms of asymptotics about what happens in the limit of taking sort of all the terms, because in general you're never going to take your entire asymptotic series in order to try and represent your function. Okay, so in general, if you do this right, then right, your remainder term here is going to be bounded. So this seemingly works like pretty well for x small enough, right? But you can see for sure there's always going to be a problem if we take 100 terms in our asymptotic series, right? Our remainder in this case is going to blow up. So the idea is to balance things so that you don't take too many terms in your asymptotic series that the divergence is going to swamp you, right? You take just enough terms so that you have a fairly accurate approximation, okay, for a small enough variable x in this case, small enough argument x in this case. Okay, so so the remainder term, right? This is our RM term, is of order of the first neglected term of s of x, right? So remember when you write down order of asymptotic series, you always drop the constant, right? If you look at this constant, that's going to be a problem, right? This constant is just going to keep blowing up forever, right? But it's not so big of a deal if you're taking a finite series and x small enough. Okay, so in general, the order of this is going to be x to the m plus 1, okay, as x goes to 0 from above. Okay, so let's summarize what we've seen now in this sort of curious example, but it's informative in general of asymptotic series. Okay, so the series Sm of x, okay, behaves like a convergent alternating series, except the smallest term in the sum, okay, for a given x determines some limit to the accuracy of Sm of x as an approximation of f of x is equal to the integral from 0 to infinity e to the minus t divided by 1 plus xt dt. Okay. So if divergence or convergence of your series with infinite terms is not necessarily a guide to the use of your asymptotic series. What is? Well, it's going to be the remainder term, okay, for however you truncate your asymptotic series, right? If you're too restrictive about what you're willing to allow as an asymptotic series, you're going to exclude a bunch of series that are potentially useful, even though they may be divergent if you take every single term in the asymptotic series, okay? So the key take-home lesson here is that asymptotic series, you should not treat them as something that you're going to take every single term in the series and then you'll converge back to the function, okay? They are practical specifically because you only want to take a few terms in the series, right? And then you get a fairly accurate approximation of your function, okay? All right. Questions about that? Okay. That's a sort of a classic guiding example, okay, that Euler sort of stumbled onto and sort of has guided a lot of the intuition for asymptotic things, okay? Let's finish off with a couple of definitions and then we're kind of done with this discussion of the mathematics of asymptotic series mostly. And then on Monday, we'll launch into integrals, okay? The definition, so the sequence of functions, f n of z, okay, for n is, let's say in the positive integers, okay, is an asymptotic sequence for z goes to z0. Okay, remember z needs to be in some domain D. If for each n, fn plus 1, z is equal to little o fn of z as z goes to z0, okay? In other words, fn plus 1 is much less than fn for z goes to z0, okay? So naturally, examples would be like, you know, 1 epsilon squared, right? Because always the next term in the series is going to be little o of the previous one. It should be smaller than the previous one. Okay. So that's an asymptotic sequence, and then the asymptotic series n equals 1, and I can truncate this, okay, to just some finite number of terms to make it an asymptotic approximation. Asymptotic approximation to f of epsilon as epsilon goes to 0 if for each m less than or equal to n, then the following thing is true. F of epsilon minus the sum from n equals 1 f to m, f sub n over epsilon divided by f sub m epsilon. This needs to go to 0 as epsilon goes to 0. Okay. Or f of epsilon is equal to the sum from n equals 1 up to m, fn of epsilon plus some little o terms of fm of epsilon, okay? So this maybe is intuitive, right? each term I add on in my asymptotic series, okay, should be of smaller order than the previous one. That's what makes my asymptotic approximation asymptotic. Okay. So and then in this case, we write f of epsilon is approximately equal to n equals 1 up to n fn of epsilon as epsilon goes to 0. Okay. So that's our asymptotic sequences and their corresponding approximations. Okay.
In the second option, should there be like an m+1 somewhere, like on the little o maybe?
This one here.
Yeah, because didn't we double count fm?
Fn. So this is just
Or is it
saying
because
that
of the little o?
this is a little o. Sorry.
Okay.
Yeah. So everything after this should be of smaller order than
Got
the
it.
last term. Yeah. Okay. All right. So so what did we learn today? So one of the main things is understanding about the importance of not excluding series that may be divergent from candidate asymptotic approximations. Okay. The point is that if you use an iterative procedure, if you use um, an expansion method, okay, you may come up with a series that's going to blow up as you add more and more terms. Okay. Don't discount that series, right? Because the key thing to look for are these order relations as you start to add on more terms, right? Of course, if you take 80 terms or 200 terms in that asymptotic series, for the particular value of epsilon that you're interested in, all of a sudden you're gonna lose validity of that asymptotic series. That's typically why for asymptotic approximations, you don't really want to go up to more than 2 or 3 terms, right? Because the coefficients may start to build up and it may swamp the value of the approximation that you made at lower order, right? So both of those things are important to heed, right? Not just the shrinking order of your parameter as or functions of that parameter as you go up in the series, but also what the coefficients are doing. So next time we're going to talk about asymptotic approximations of integrals, and the important thing there is that depending on what method you use to approximate an integral, it may be that you end up with a divergent series, okay? But you end up with an asymptotic approximation that's way, 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 way better for 1 or 2 terms, okay, than necessarily a convergent series would be, okay? And that's key to think in mind. So we're sort of moving away from the notion of asymptotic series just always kind of being like Taylor series, right? Or convergent series that you would come across in calculus, right? We're moving into the realm of divergent series that nevertheless you can truncate and make them extremely useful. All right. Any questions or comments before we wrap up for today? Okay. All right. So I know the last few weeks we've sort of moved through what may feel sort of preliminary. I hope that once we start getting into integrals, these are really the types of things that you're going to encounter in research problems, solutions to mathematical models, and then even more so maybe when we get to differential equations. So I'll post homework 2 after class. That'll be due on in 2 weeks time. And then I had one more thing to say. Oh yeah, just recapping. So yeah, the homework was due today. I should definitely have it all marked in a week, but I'll post my solutions later today as well if you want to take a glance at those. Okay, thanks everybody. Have a good weekend.
Okay.
Zach,
Yeah,
so since this series doesn't converge, uh, I would expect that we can't take arbitrarily many terms in this finite sum and in this partial sum to approximate it.
for sure.
So, how would we know how many terms we can take?
Yeah, the guide is your remainder term. So if we look here at our remainder term, right, you can bound your remainder term. And you can say, I want this asymptotic series for, maybe x is 0.01. What does it say that my remainder term is going to be in that case, right? And then you can actually take the value of m that's going to minimize that remainder term. So sort of set it up like an optimization problem. What's
Oh,
the value of m that's going to, because now you have competing forces, right? So this thing's growing, but this thing's shrinking. Okay, what value of m sort of balances that trade-off? Um, that's the idea. So the key thing to look at is your remainder term and not some general result about convergence or divergence of your series once you include infinite things.
so we sort of approach this starting with the series. Um, but I suppose, like in practice, we would start with the function f that we would want to approximate.
Yeah, we could go the other way, right? I mean, we're just not quite into asymptotics for integrals yet, but I could have gone the opposite way, right? So and you can use integration by parts, for instance, to get the asymptotic series S of x from this,